result that we want to prove about the sigma function. So let's talk about what the sigma function does first of all. And it's put simply, it's just the sum of all the divisors of any integer, positive integer usually, I think. Now, 1 is a divisor of any integer. Now for 6, 2 is also a divisor. 3 is also a divisor. And the number itself. And y'all really, I should be putting plus in front of that, sorry. This is plus, forget the commas. Plus, plus, plus. And notice that adds up to 12. Now this ends up being a famous number, not that it's related to how we solve this problem. It's the first perfect number because it's equal to the sum of its proper divisors. 1 plus 2 plus 3 is equal to 6. Okay? But in any event, that's what the sigma function does. It sums the divisors. Now we want to prove something that's sort of counterintuitive. We're taking an input that's 3 less than another input and claiming you can find an infinite number of such inputs that meet this condition, where in other words, the sigma of a smaller number is greater than sigma of n. You could understand it happening a few times, but it happens an infinite number of times, and that's what we're going to prove. Okay. Now the sigma function itself is not an increasing function, but it kind of increases in groups, if that makes any sense. So if you look at a graph of it on some software, it does gradually grow, but it's jagged. It's not an increasing function by the strict definition. Okay. So now, an important result that we're going to use is that sigma of n is equal to n plus 1 whenever n is prime. That follows immediately from the definition of a prime number. Let's say 23, that's a prime number. Sigma of 23 has 2 divisors, namely 1 in itself. So that's equal to 1 plus 23, which is equal to 24. Okay. And literally, the sigma function, if you defined it first, you could define the prime, what it means to be a prime. The prime numbers are the only ones that have this particular property. Okay. Now, there's another thing important to note right here. 3, 5, and 7 turn out, they're the first. 2 is also too small. I just listed 3, 5, and 7. I probably should have put 2 in there. But notice that if you put 2 in here, you get sigma of -1, which we're not interested in. It's defined on the positive integers. Sigma 3, if you put a 3 in here, you get 0. Let's just look at 7 as an example. What if n were 7? Just to let me show you why I excluded these guys. If n is equal to 7, this becomes sigma at 4. Putting a 7 right here. And this is equal to 1 plus 2 plus 4. Okay. Now over here we have sigma at 7. And of course we've already seen what that is. That's equal to 8, right? So you see that's why we can't use these particular prime numbers. Okay. This is what 6, 7 is not greater than 8. Okay. Now, so let's proceed here. We're gonna use all the primes greater than or equal to 11, and a prime is an odd number. Now, a prime being an odd number, when you subtract 3 from an odd number, you get an even number, and this actually should be n plus 3 right here, folks. Sorry, n plus 3. My bad. Let me write that in there a little bit better. N plus 3. Now, why is that the case? Let's just take a look here. If you have an odd number, let's call it 2k plus 1. Okay. Now, notice that if you subtract 3 from this, minus 3, you just get 2k minus 2. But that's 2 times k minus 1, which is an even number, right? So there's your quick proof of that, right? It's something that's very believable. But again, if you subtract 3 from any odd number, it's going to be in the form 2 times some other integer. In this case, it's k decremented by 1, okay? Now that's important because n plus 3 being even for k greater than or equal to 4, and that comes from the fact that just n is 11, okay? So we can list the divisors of n minus 3. Y'all, sorry, this is a -3. My bad right here. This is a -3. That's -3. Sorry about that. I just didn't write that in. Okay, so the divisors of n-3 are the number itself, n-3, and then this 2 and this k is, see this 2 right here and this k right here is exactly where I get this divisor, and you got 1. Now, when you sum all of that up, when you sum all this up, you do get n plus k, but notice we've shown that k is greater than or equal to 4. So this is greater than or equal to n plus 4. Okay? Greater than or equal to n plus 4. All right, now, so we know exactly what that, let me just write it down here to get it kind of in a neat place here. So we know that sigma at n-3, as long as n is a prime greater than or equal to 11, okay, is greater than or equal to n plus 4. Now, of course, we want to compare this to sigma at n, all right, because remember, what are we trying to prove? We're trying to show that we can find as many n as we want to, such that sigma at n-3 is greater than sigma of n. Okay, so let's see, what's sigma of n? Well, n is known to be a prime, right? So sigma n is just equal, just like the definition we wrote down a while ago. Okay. And again, y'all, that is because n is positive to be a prime number, namely a prime number greater than or equal to 11. So we can see right here that manifestly, this is always greater than or equal to n plus 4, and this is fixed at n plus 1. So we can see that sigma at n-3 is strictly greater than sigma at n an infinite number of times, folks. And again, that I've written it down back up here, but it's when n is greater than or equal to 11. Let n be a prime greater than or equal to 11. So this happens. There's an infinite number of those numbers. So this is an infinite number at time. Infinite number. I'll just write it infinite number of n. And specifically, those n are 11, 13, 17, 19 ad infinitum. Okay, so we can write QED. And y'all, a lot of you who are interested in this kind of stuff might note that the way this was proven indicates we can pick any arbitrary natural number. Like you could find a prime number for 4, prime number for 5, 6, all the way. So in other words, you could always find an infinite number of n such that n minus an arbitrarily large natural number, that the sigma value of that's always going to be greater than sigma of n. Which is very interesting in my opinion. But it's, if you think about it, it's a fairly natural thing to believe once you see the proof, because there are an infinite number of primes. Okay, so that completes the proof. Thanks for viewing.